Hey everyone, so it's been a while since my last video, and that delay has been in part because of something I want to show you today. Recently, I've been developing a set of plotting tools for OpenSees with Anurag Upadhyay from the University of Utah, and these have been integrated into the OpenSees base package. So in this video, I want to walk you through some of the new post-processing tools that have been introduced to OpenSees. You can see right now we're actually looking at a plot, and this is from the tools. So this is an OpenSees model. It's kind of just a set of 2D shell elements. We can see like the nodes, the elements in the model. There is also some other things that you can do, such as if you want to take a look at the mode shape of your model, there's tools for that. And also if you want to say plot the deformation of your model over time, there are tools that let us do that. In this tutorial, I'm going to take a look at two examples. I'm going to take a look at this kind of basic 3D model that's been created with shell elements. And I'm also going to take us through the cantilever truss that we looked at last time, so we can see how we can use some of the new plotting features for fiber elements as well. Okay, so let's just start by making sure that you have all of the files necessary. Because this is part of the base OpenSees repository, you can get the necessary files just by upgrading your OpenSees if you haven't already. So we can do something like pip install OpenSees py, and this is of course, I'm assuming you're using Anaconda. So in Anaconda prompt, we can do this, and then upgrade, and then you'll see I already have the most recent version. So on your side, you should see it upgrading if you don't have it. I have a whole bunch of errors because my Anaconda environment is really weird right now. So you shouldn't have these, but that's all you'll need to do to get running with the most recent version. So now let's just look at the folder structure that I'm going to use for this tutorial. I'm going to have two folders, one for the 2D fiber model and one for the 3D model. I'm of course going to include a link to these models in the description, so if you want to follow along, that's probably a good idea. But I would also suggest if you have your own model, this might be a good time to try to see if this will work on the model that you're testing right now. But we'll start with just the 3D model, and I'm going to have the shell 3D element in here. So let's get going and open up Spider. Opening up the file, we should see something like this. So we're importing OpenSees as OPS. I think I've finally lost my battle on having this as OP, but that's okay. OPS is probably the standard from here on out. So, and then we're also going to import post-processing. So we're going to import post-processing, the get rendering module. So this is where everything we'll be working on is as OPP. And let's just start. You should try and run the script and just make sure it works so you can see, okay, it runs well. We don't really care too much about what's actually going on in this script, but to give you a basic idea, it was by Andreas Schellenberg, and Andreas has applied some forces to the model and then released the forces and performed a transient analysis on the model once it's complete. So if we want to see what's going on in the model, very simple. We'll just do OPP dot, and we'll go, where are you? It's plot model. So plot model like this. So we don't actually need any commands. Right now, you'll note we haven't actually cleared our model, so the OpenSees model is still in the buffer. So if we run our command now, we will see this nice output of the graph. So some things that you can do if you're using Spider. Right now the plot is showing up inline. If I want it to show up in its own separate window, I can type the command matplotlib qt like such. Now that changes the backend of what Spider is using to plot the elements. So if we run it now, instead of showing up in the window over here, it has its own separate window. So every time you open up Spider, you'll have to type this command. If you want, by default, if you want to have it so that by default a separate window will pop up, you can go to Preferences, as I was struggling to do, and in the IPython console option, if you go to Graphics, you can change the backend from inline to Qt by default. So if you want to do that, that's an option. Command has a few options. If you want to display the nodes in the model, you can give it the nodes argument, and if you want to display, if you want to display numbering for the nodes, we can give it nodes, and we can give it the element tag. And then running this, we'll see we now have our model, and it's showing where the tags are for the. It's showing the tags for the model. We can also run a few other commands on the active model. The most notable is going to be the plot mode shape. So this is going to take the first mode, the first argument is going to take is the mode shape, and then the second is going to be the scale factor. So I'll just use 2 to see the second mode and 200 to scale it by 200. And let's just run that and see what comes up. So we can see this is the mode. We can see the period for the mode. And we can also see like an overlay of what the base shape of the model looks like. So if you're feeling a little overwhelmed and not sure what arguments that these functions can take, we can just go to the OpenSees Wikipedia, and you can see for all of these commands, we do have documentation. So if you're wondering what you can pass to these commands, there is the relevant documentation there. So just know you don't have to have all of this memorized. You'll note for everything that we've been doing so far, we have needed the model to be active. This can be kind of inconvenient because obviously we don't want to be running everything. We don't want to be creating our, like sometimes we're going to want to see what our model looks like without having to run our analysis. And you can see if we were to say issue the wipe command here, we would end up with an error. So there's actually been a new feature that we've implemented, which we're calling the output database for the model. So you can create and use an output database to store information about the model, which will later be called by the plotting functions. So let's create an output database for our model now. So the command for the output database needs to be issued at a very specific time in our model creation. It needs to be created at some point before the analysis is run, but after the model is already in the active buffer. So the best place to do that is going to be probably between where you create the model, so where you create the loads, and where you run the analysis. So in our case, we're setting all these analysis parameters down here. This is probably where I'm going to want to create the model, the output database. So the database will need 2 parameters. It will need a model name, so we'll create variables for that. Model name, and we'll call this a 3D shell, and it's going to need a load case name, and that will be transient. Yeah. So we're doing a transient analysis. You can have multiple load cases for each model, as we'll see in the future. But now we should be ready to actually issue the command. So we'll create the output database. See, I get a nice suggestion for that. The first argument is going to be the model name, and the second argument is going to be the load case name. We also have some keyword arguments we can issue to it. So we'll tell it that we'll ask for the first 3 modes for a structure. So we'll say number of modes equals 3, and then we should be good to go. Again, if you're wondering what commands you can give this model, there's documentation on the OpenSees Wikipedia. But so this will be good for our purposes. So let's just run this and see what happens, and then I can kind of take you through the results. So let's take a look at the file folder. If you look, we can see we now have this new folder entitled 3D Shell OBD. So this is our output database for the model. And if you look in here, there's a whole bunch of information that's been stored about the model. We have information about the elements and the nodes that are connected to it. So each of these elements files will contain a list of all the elements as well as which nodes are connected to it. And this node output file will contain a list of the nodes and the XYZ coordinates of all the nodes. You don't necessarily need to understand what's going on in all of these files, but it could be helpful if you want to, say, use them for your own purposes. All of the functions that we're going to be using will basically just reference the information that's stored in this output database. Like, for example, we can we can tell that the mode shape command, we can tell it to read from the output database. And then instead of needing to have the model active, we can plot it at any time, which will be useful. So you'll also note the transient. This is the load case. So if we were to, say, create a different load case, we would have another folder specifically for that. And here we have the displacement of all the nodes in the output file. So let's just try and set up our functions. So instead of reading from the active model, they're reading from the output database. So we can do that super easily with this keyword argument. We can say model, and that will equal our model name. And that's all we have to do. So now we'll do the same thing for the plot mode shape. And now when we run this, we should see our plots, and we should not have an error. Okay, perfect. Before I go on to any other plotting commands, I want to show you something, a challenge that you might encounter when you're just using the output database like this. With our time step in the model, right now this is actually a fairly big time step for any sort of transient analysis. So 20 milliseconds. But you might end up having to use a time step that's a lot smaller in your models. And in this case, we might end up with a lot of data, which is pretty undesirable because it will take a lot longer to work with, to save the outputs, and really we don't need all that data. So just to kind of highlight this, I'm going to change this from 20 milliseconds to 1 millisecond, and then instead we'll do 2,000 time steps, and we can just run our model. It'll take a little bit longer to run, of course, now because we have 2,000 time steps. But if we look at our output, just to kind of highlight what's going on, these files are now way bigger. And if you're just wanting to plot the model, you don't really, this is all data that's kind of superfluous. We don't need to have 2,000 data points at 1 millisecond just to have a general sense of what's going on in the model. So what we can actually do is we can create a different time series, and in fact you probably wouldn't even want to have the original one, so you'd probably replace that with something like this. So we'll issue a command called delta t, and we'll say it's 0.2 seconds. In this case, we'll change the load case name, so load case name 2, because I'm just being kind of quick, not giving it a proper name. So we'll call this transient 2 milliseconds, and then we'll run the analysis. So what this is going to do is, instead of saving every single output, it's only going to save outputs after every delta t time steps. So if we look at the model now we can see there's two cases: the transient one, which is it still has all the data at every single time step, and then the transient 2 milliseconds. We can see this is way smaller, and we can see that it's only plotting about every 2 milliseconds. It's not going to be perfect. Basically, the way that it looks is it tries to find the time step that's closest to these 2 milliseconds. So you can see that sometimes it's finding a time step that's slightly different than maybe what we wanted it to, but generally it's the value is pretty much close enough. So when we go to do our animation or something like that, we can be pretty content with the outputs. So that's just something you can do to reduce your data, because realistically, if you have a big model, you don't want to be saving at every single time step, because you're just going to have way too much data. The next command we'll be looking at is going to be the deformed shape command. So we can plot the deformed shape of our model. In order to do this, we need to have an output database now. So this command will not work on the active model, because obviously we need to know about the deformed shape in order to plot it. And to know about that, we need to have the output. So we're gonna, oh, stupid, come on. I'm gonna attempt to plot the deformed shape. Okay. So this command will take the model as an input. We'll also take the load case. So we'll do our transient load case. We have a few optional arguments: time step, scale, overlap. So by default, it's plotting the final time step. Well, we're going to bump up the scale to 200. That was what we were using for the mode shape. So I think this is going to be pretty good. We'll see. And then, oh, sorry, model name. The first variable should be model name. So yeah, let's just try this. We should be good to go. Oh, scale shouldn't be capitalized. And yeah, sorry, I'll make this, I'll make it a Qt backend again. Been restarting my console a bunch. So yeah, perfect. So we can see the final deformed shape. What we could also do is we could specify a time in our model to get the deformed shape at that time. So let's say now, I'll close these guys. Let's say now we want to have the deformed shape at time, so time step, and let's say just 0.5. So this it will look and it'll find us the time shape, the time step that's closer to it, and it'll plot that. So we can find, in this case, looks like it found exactly 0.5 seconds. If we give it something kind of funky like that and plot it, it will see it couldn't find a time step at 5 point whatever, but it could find one at 5.2, and I figured out that's the closest one. So yeah, that's the deform shape command. I'll show you if we also so the overlap, what that is doing is if we say yes, then we can just see the original shape in addition to the deform shape. The final command I'll show you will be the animation command, or the animate deform shape command. So this command, similar to the plot deform shape, we're going to need to have the model information because it reads from the output database. So we need to have created an output database. And we're also going to give it a DT. This will be the target time between steps. We'll just use the animation dt for now. Or excuse me, the analysis dt. And we'll also give it a scale. We'll just say 200. That's what we've been doing for the last few. So the scale is equal to 200. In order to run this command, you will actually need to return an animation object. So it's a little bit different from the other commands. We'll return the animation as a variable like this, and now when we run it, we should see the outputs. Perfect. So we can see our model. We can see it deforming over time. So you might note that this is a little it's a little bit slower than real time right now, the animation, which maybe is fine for your purposes. If you want to get it as close to real time as possible, what I would recommend is that you create a load case, and so the animation is going to display at a certain frames per second. We're using 24 frames per second. Anywhere between 24 and 60 is probably good. I don't think it's reasonable that you can actually get like a 100 frames per second animation, just because the way matplotlib works in the back end, you probably won't be able to from a performance perspective, you probably won't be able to render that many frames anyways. But yeah, by default, it's at 24 frames per second. You can see right here. So we'll just leave it like that. And then I think, like I said, the best that we can probably do to get it as close to real time is we're going to set the time step in this load case to be 1/24, so because that's our frames per second. We'll also set that to be our dt. And we will change the load case that we're reading from. So we'll read from the one with 1/24 frames per second. Now if we run, we'll get something that's reasonably close to real time. I do want to caution, there is a known bug when we implement this DT in our recorders. Sometimes the frames are going to be skipped. And this skipping of frames can lead to some errors. So right now you will note our animation ran for 0.2 seconds, but because of some funky stuff that's happening in the back end, there are some frames that are being skipped over, some intermittent frames that are being skipped over. So this 0.138 is actually the final 2 seconds. And it's just intermittently some frames have been lost because they're being skipped by the recorder command. So just know that this is something that you can get into, and this will particularly affect us if our time step is not particularly big, or excuse me, if our time step is particularly big. As we start decreasing the time step, this will become less prominent. So if I go and I decrease my time step, we can see that we are actually able to get pretty close. We can see that it's skipped a lot less frames, but just know that right now this is a known issue. So it's only if you're trying to get an animation that's close to quote-unquote real time. So that's it for this video. In the next one, I'm going to spend a bit of time on the fiber sections in 2D, so we can take a look at some of the outputs of those models, which hopefully will be interesting to see. These functions are all under active development, so if you have any thoughts or ideas, hopefully we'll be adding a lot of really cool new features to them as time goes on. Right now these are all on plotting deformation, but I'd really like to be able to do things like plot forces, stresses and strains, things like that. So hopefully there'll be a lot more cool things for you to see in the future. And definitely check out that second video if you want to see how to plot the outputs of fiber sections.